Welcome to Math 108. I am Dr. Diana Songsong, your teacher for this course. The primary goal of this course is for you to learn the process of proofwriting so that you might have the skill set necessary to continue on your journey in mathematics. In this course, we will begin by studying the basic rules of logic as well as some common types of proof arguments. To start our discussion in logic, let us first define what a proposition is. A proposition or a statement is a declarative sentence that is either true or false but not both. We call this the truth value of your proposition. We often use capital letters to denote propositions. So for example, the number pi is greater than 3.14 but less than 3.14. This is a proposition. In particular, its truth value is true. Next, the integer 91 is prime. This is a proposition with truth value of false because 91 is equal to 13 times 7. The integer 0 is an even integer. Yes, this is a proposition. This one here is true. The following are not propositions. Solve the equation. This is not a proposition because this is an imperative sentence or a command. Remember that a proposition has to be a declarative sentence. What is the derivative of f of x equals x squared? This is an interrogative sentence, so therefore not a proposition. This problem is unfair. This is an exclamatory sentence. Take note that a declarative sentence is still a statement or a proposition even if we do not know whether it's true or false. For example, in the decimal expansion of square root of 2, some digit appears 100 times in a row. I do not know whether this is true or false, but definitely if you use a computer, you will determine whether it is true or false. It's just one of the two. Let us identify whether these are propositions or not. I interchangeably use propositions with statements, so please take note that they are just the same. Sine pi over 2 is less than sine pi over 4. This is a proposition. In particular, this is true. Next, chocolate ice cream is the best ice cream flavor. This is not a proposition because this is just an opinion. It can be true for some but false for other people. Next, number 3, look out. Of course, this is not a proposition because this is an exclamatory sentence. Number 4, she lives in New York City. This is not a proposition because you have the word she here. You actually call this an open sentence. We do not know the antecedent of she. We do not know who it refers to. This statement is false. This is also not a proposition. In particular, you call this a paradox. Why is that? If this statement is true, let's say that this is true. But if this is true, then it's saying that this statement is false. So you will have a contradiction. If it is true, then it is false. Correct? However, if we say that the statement is false, then this statement is true. It always contradicts itself. So we say that that is a paradox. Next, the slope of a vertical line is 0. This statement here is false, correct? So therefore, this is a proposition. Next, x plus 1 equals x minus 1 times quantity x plus 1. Take note that you have the presence here of variables. This one has variables. And if it has variables, it cannot be a proposition because again, just like with number 4, we do not know what x is. This is also an example of open sentence. We will deal with open sentence in our succeeding lectures. Next, number 8, for every angle t, cosine squared t plus sine squared t is equal to 1. Take note here that although you have the presence of variables, you defined what that t is. T there is an arbitrary angle. This is what you call a quantified statement. and therefore this is a proposition. In particular, what is the truth value of this? This is true. We will tackle quantified statements in our succeeding lectures. Since we are interested with the truth values of statements, we look at all the possible truth values and we call that our truth table. So here are examples. If you have just one proposition, the only possibilities are true and false, and so on. If you have two propositions, P and Q, you will have four possibilities. And then if you have three propositions, you will have 8 possibilities. Why is that? If you use the fundamental principle of counting, if you have 3 variables, P has 2 choices, true or false, Q has 2 choices, and R also has 2 choices. So therefore, you have 2 times 2. So that's 8. So in general, if you have n propositions, how many rows should you have? You should have 2 to the n rows. That will tell you the number of possibilities. Propositions are just like numbers. You can combine them. So to combine propositions, we use logical connectives. Logical connectives are operators that are used to combine one or more propositions. We will be tackling 5 logical connectives: negation, conjunction, disjunction, conditional, and biconditional. For this video lesson, we will be tackling these 3 logical connectives. Let us start with the negation of a proposition. Suppose that we have a proposition P. The negation of P, denoted by this, we read this as not P. The negation is the proposition that has the opposite truth value of P. Thus, if we look at the truth table here, if P is true, not P should be false. If P is false, not P should be true. For example, let us get the negation of the proposition Q. The number 91 is a prime number. What is its negation? The number 91 is not a prime number. Another example, the integer 0 is an even integer. Its negation is the integer 0 is not an even integer. Or you can also say that the integer 0 is an odd integer. Because if you're not an even integer, you are definitely an odd integer. Next, the number square root of 3 is an integer. Its negation is the number square root of 3 is not an integer, or you can also say that it is not the case that square root of 3 is an integer. Let's go to our second logical connective, conjunctions. The conjunction of the statements P and Q is the statement P and Q, and it is denoted by this. You read this as AND. It is true only when both P and Q are true. Otherwise, P and Q is false. Let us create the truth table of this. If you have 2 propositions P and Q, the possibilities are 4, TTF and TFTF. So therefore, this is saying that it is only true for the first row, and for the rest of the rows, it will be false. Suppose that P is the statement square root of 2 is less than 1.5 and Q is the statement pi is equal to 22 over 7. What is the truth value of P and Q? In order to determine the truth value, let us get the truth values of its components, P and Q. Square root of 2 is less than 1.5. This is true. Square root of 2 is approximately 1.414. What about Q? This is false. Pi is just approximately equal to 22 over 7, but they are not equal. So therefore, P and Q is false. Take note that the English words but, while, and although are usually translated symbolically with the conjunction connective because they have the same meaning as and. In the English language, we are using these words to just show contrast. But technically speaking, it is just the same as and. Suppose that we have the statement, Lara is pretty but disorganized. This is just saying that Lara is pretty and disorganized. I just used the word but because this is something which is a positive trait and this is a negative trait. For example, the number 9 is not composite but 45 is a multiple of 3. So if I make P be the statement 9 is composite and Q is the statement 45 is a multiple of 3, then this statement becomes not P because 9 is not composite, but that means and 45 is a multiple of 3, so that's Q. Next, let's go to disjunctions. The disjunction of the statements P and Q is the statement P or Q, and we denote it by this symbol. The disjunction P or Q is true if at least, take note, you only need one of them to be true. Recall that at least means you can have more than one. So therefore, how will the truth table look like? On the first row, P and Q are both true, so therefore, P or Q is true because it says that at least one. We have more than one, so that's good. That's even better. Here, P is true, so this is true. Here, Q is true, so this is also true. It will only be false when both are false. Suppose that we have the same statements as before. What is the truth value of P or Q? We've seen earlier that P is true and Q is false. One of them is true. So therefore, P or Q is true. Take note that if both P and Q are true, P or Q is true, right? We've seen that in the truth table. This is not the way that the word or is usually interpreted in the English language. So for example, if I say, you may have an ice cream cone or you may have a candy bar. In the English language, we mean that you can only have either one. If you have an ice cream cone, then you definitely can't have a candy bar. If you have a candy bar, then you cannot have an ice cream cone. However, for the mathematical or, we mean one of the two or both. This one, P or Q or both. Suppose that we have the statements P and Q. P is the statement the number 19 is composite and Q is the statement the number 45 is a multiple of 3. Let us express the following statements in English form and find their truth values. For P and Q, of course, what is this? The statement is the number 19 is composite and the number 45 is a multiple of 3. Let us determine the truth value of P first. 19 is a prime number, so this is false. 45 is a multiple of 3. This is true. So therefore, P and Q is false. Next, P and not Q. So this means that the number 19 is composite and we have not Q. The number 45 is not a multiple of 3. What can we now say about the truth value of P and not Q? P is already false, so automatically this is false. Next, not P or not Q. The statement becomes the number 19 is not composite, or not Q is the number 45 is not a multiple of 3. So in this case, not P is true because P is false, so this is true. Not Q is false because Q is true. Since I have one true statement, this statement here is true. Let us determine the propositional form and truth value for each of the following. What I mean by writing the propositional form, it just means that I want you to write it in symbolic form. So for example here, I will just let this to be P, and this is my Q. So therefore, the propositional form is P or Q. Let us determine the truth value. 3 plus pi is rational. That is false. Pi is irrational. So even if you add 3, that will still be irrational. Next, 3 minus pi is irrational. Pi is irrational. So therefore, when we have 3 minus pi, that is still irrational. One of them is true. So therefore, the whole thing is true. Next, it is not the case that 39 is prime or that 64 is a power of 2. So let this be P. And then here, 64 is a power of Q. Notice here that you have a comma. This one is saying that the it is not the case just goes for P. So we have not P or 64 is a power of 2, Q. Let us determine the truth value. 39 is prime. This is false. 64 is a power of 2. This one here is true. So therefore, for not P is true. Q is true. Both of them are true. We only need one to be true because this is OR. Therefore, the entire statement is true. Next, the graph of f of x equals e to the x is increasing and concave down. So here we can say that P is the statement, the graph of f of x equals e to the x is increasing. And we take Q to be the graph of f of x is concave down. What is now the propositional form of number 3? That is P and Q. The graph of f of x is increasing. That is true. But it is not concave down. It's concave up. Q is false. So therefore, P and Q is false. For this next two examples, we always have the same propositions here. Square root of 2 is rational. Square root of 2 is greater than 1. And square root of 2 less than 2. I will let this be P. This is Q. And this is the statement R. For number 4, you have a comma here. So this means that we have P, and then look at this one, and either. For the either, this one will be joined. Either Q or R. Again, let me just reiterate that the comma tells you where the parenthesis is. Next, for this one, the comma is in here. This is P, this is Q, and this is R. So therefore, what is the propositional form? We have P and Q. The comma is there, so we have a parenthesis here, and then OR. I have OR R. What are the truth values? Let me just write the truth values here. Square root of 2 is rational. That is false. Q. Square root of 2 is greater than 1. That is true. And then R. Square root of 2 is less than 2. Yes, that is also true. So therefore, for number 4, Q or R is true. So this whole thing is true. P is false. So therefore, this entire statement is false. Next, for number 5, P and Q. This is false because P is false. R is true. So one of them is already true. So therefore, this is true because we have the connective OR. Next, it is not the case that both 2 and square root of 2 are rational. So for these 3 examples, I will let P be the statement that 2 is rational, and Q is the statement square root of 2 is rational. P is true. Square root of 2 is rational. That is false. So therefore, for this one, number 6, it is not the case. So that means we have negation. It is not the case that both of these are rational. So it is not the case P and Q. What is the truth value? From here, P and Q is false, correct? Because P is true, Q is false. So this one here is false. The entire thing is false, and therefore the negation of that is true. Next, we have neither 2 nor square root of 2 is rational. When we have something of this form, neither A nor B, this is actually saying that not A and not B. So therefore, this one is saying that 2 is not rational and square root of 2 is not rational. So therefore, what is the form? 2 is not rational, that is not P, and square root of 2 is not rational, that is not Q. What is the truth value of this one? P is true, so therefore not P is false. Q is false, so therefore not Q is true. So therefore the entire thing is false. Next, either both 2 and square root of 2 are rational or neither of them is. If we look at the form of this statement, this is an OR statement, and the two components are this and this. So that means that this is for your first component, then you have OR, and then this is for your second component. Neither of them is. For the first component, both 2 and square root of 2 are rational. What is that? That is the statement P and Q. And then for this one, neither of them is. That is actually number 7. Neither 2 nor square root of 2 is rational. We already obtained that that is not P and not Q. Let us determine the truth value for the first component, P and Q. P is true, Q is false, so therefore this whole thing is false. For this one, not P and not Q, we found in number 7 that this is false. So therefore, both of these two components are false, which makes this one false. Next, if P, Q, and R are true while S and T are false, determine the truth values of the following. Okay, so let us start with the innermost. R and S. Let me just write it here. P, Q, R, S. These are true, true, true. S is false. So we have R and S. R is true, S is false, so therefore R and S is false. Q is true. So one of them is true, so therefore this is true. Next. For this one, not P or not Q. Not P is false because P is true. Not Q is false. So therefore this whole thing here is false. Not R. R is true, so not R is false. Not S. S is false, so therefore not S is true. One of them is true, and we have OR here, so therefore this is true. So for the two components, the second component is true and this is joined by OR, so therefore this is true. In these examples, we are actually discussing compound statements. What are compound statements? These are just statements that has been built by applying at least one logical connective to one or more statement. In our previous examples, we combined Q, R, and S using the logical connectives OR and AND. For example, let P and Q be statements. The statement P and Q or the negation of P and Q is a compound statement with components P and Q. If we will make a truth table for this statement, how many rows will it have? Your main components are P and Q, so therefore, how many rows will it have? It will have 2 raised to 2 rows. We will end this lesson by making truth tables. Let us recall that a compound statement with n components will have 2 to the n rows. Let us create a truth table for P or not Q or R. So what are the columns? Of course, we have the components P, Q, R. And then we have not Q here. And then once we have that, we will be needing a column for P or not Q. And then lastly, for the entire P or not Q or R. Let us fill in the different possibilities for P, Q, and R. Half of the rows will be true for P. Half will be false. These are all the possibilities for P, Q, and R. And then for not Q, just the opposite of this column. Next, for the column P or not Q, so for the first 4 rows, P is already true, so definitely this will be true because one of them is already true. For the 5th row, P is false, not Q is false, so OR is false. And then here we have false, false, so this is false. Here not Q is true, so this is true. Here not Q is also true. For the last column, we are looking at the columns of P or not Q and the column for R. For the first 4 rows, take note that the first component P or not Q is already true. So this is true. For this one, R is true. So this is true. Here, both of them are false. So this is false. And for this one, P or not Q is true. So that makes the entire thing true. So therefore, this is the truth table for this form.